But they were about to face another danger, one that would threaten their own lives. The 25th of November 1995 was the 30th day of dredging for the Oresund link. Digging up the 7 million cubic meters of seabed seemed to be a fairly straightforward assignment, and the crew thought everything was going smoothly. But dredging had just become the most dangerous part of the entire project. Workers didn't know it, but they were just centimeters away from death. The problem started when the Chicago accidentally scooped up a dangerous payload, a bomb that was ready to explode. It then dumped it onto a barge covered in mud. Nobody knew it was there. If anything had bumped its detonator, 36 kilograms of TNT would have blasted the barge and crew to pieces. How it ended up here is a story that dates back 60 years. In May 1945, Denmark was celebrating the end of World War II. The British Royal Air Force put on an air show over Copenhagen harbour with live bombs. Some sank without exploding, and now, 6 decades later, they're more deadly than ever.
Even though the bomb is maybe 50, 60 years old, it can still work as designed. So that's why it's dangerous, always. If the bomb has gone through some corrosion and there has been some deterioration of the explosives, it may have become even more sensitive, and in that case, even more dangerous.
Equipment inched closer to the bomb. Then, just in time, someone on the dredging team spotted it. The Royal Danish Navy was called in to remove, defuse, and explode the bomb. These bomb experts knew better than anyone that the outcome could have been tragic.
If they hit the bomb with their dredgers or with their buckets or whatever, and it went off, somebody had been killed.
It was a narrow escape for the crew and the schedule. With the bombs gone, dredging resumed. But the relief was short-lived. Soon, more bombs were discovered. Luckily, no one was injured, but the schedule suffered huge setbacks. Now, no area could be dredged until it had been swept for bombs. All 16 were removed and destroyed. Being safe was more important than being on schedule. Long before the bombs had been discovered, and even before a dredger had dipped its first bucket, the Oresund engineers knew they faced a unique set of very difficult challenges here. The water separating Denmark from Sweden was 16 kilometers across, but the cultural gap between the nations was much larger. They were two very different countries, with different languages, currencies, and ways of doing just about everything. Cars didn't even drive on the same side of the road until the 1950s. And trains still don't, passing on the right in Denmark, but on the left in Sweden. They also run on different electrical voltages and use different signals and radio frequencies. None of this had mattered before, because the countries had never been connected. But now it was a puzzle that needed to be solved before the bridge could open. Engineers needed to design a computerized Rosetta Stone so that the different train computers could communicate. They also needed to create a standardized wording so that all train operators would understand spoken instructions. And designers had to invent electrical equipment that would switch trains from 25,000 volts to 15,000 volts on the fly. The solutions were so complicated that every new train would need to be tested without passengers before it could use the Oresund link. But there was also a problem with emergencies. Firefighting equipment in one country didn't fit equipment in the other. The best solution was to put both couplings on every water hydrant. Every little detail required collaboration. The countries didn't even use the same name for the strait. The word Oresund is a mixture of the Danish and Swedish versions. While some of the team worked on a name for the link, others continued to work on how in the world to build it. The plans called for a submersible tunnel bigger than any ever made before. The first step was to construct a factory to make tunnel parts. The idea was to make the tunnel in 20 segments, then assemble them in the trench. Even the segments would break world records for size. They were 175 meters long, 38 meters wide, and 8.5 meters high, with 2 tubes for traffic, 2 for rail, and 1 for emergency escape. One enormous segment had to be created every month for 20 months. In Denmark, the tunnel construction began with 40 million kilograms of reinforced steel bars. These were bent and welded into a huge steel cage, then slid into an enormous mold. Then the massive framework was encased in more than 7.5 trillion liters of concrete. Of all the monstrously large parts of the Oresund link, the tunnel elements were by far the biggest. They were nearly the length of 2 football fields and as high as a 3-story house. A single piece weighed an astronomical 55 million kilograms. Moving them was an enormous and dangerous challenge, one that triggered the most catastrophic accident of the entire project. Each tunnel segment weighed more than the equivalent of 24 space shuttles. Between them, they contained enough concrete to build a pavement around the Earth twice. No machine in the world could lift one into the air and put it into place. And these engineers had to get each 55 million kilogram piece off dry land and into the middle of the Oresund Strait. The answer was to turn them into rafts and sail them. First, any holes were plugged with giant steel plates, each weighing more than 3,000 kilograms. These enabled the gigantic concrete structures to float, but there was still no way to transport them to the water. So an ingenious lock system was built to bring the water to them. The end of the assembly line was surrounded on 3 sides by dikes. The 4th was closed by a huge movable wall, and the basin was flooded to more than 9 meters above sea level. It took 100 million liters of water. Even when afloat, 4 23,000 kilogram winches were required to move each segment, and 2 more winches to steer it to the deep end of the basin. When the water returned to sea level, the segment was ready to head out. Then, when it was over the trench, there was a new challenge: sinking it. Forcing a raft this big underwater was not an easy task. The trick they used was ballast. Water was pumped into special tanks very slowly and evenly to keep the segment horizontal. 4 massive cables helped guide its descent. Precision was paramount, so it could be accurately connected to the rest of the tunnel. Winch operators used GPS and depth gauges to make sure they kept on target. The margin of error was less than 1¼ centimeters in any direction. Divers installed a temporary frame to help guide it. Then, when it reached the seabed, winch operators pulled it tight against the previous segment. Any seawater trapped between the segments was pumped out. The steel panels were removed, and to keep the tunnel from ever floating again, concrete, almost a meter thick, was poured the entire length of the roadway, then boulders piled on top. The system worked flawlessly for the first 12 tunnel segments, but the 13th still got special handling. It was officially numbered 12A for superstitious reasons, but unfortunately renaming it wasn't enough. On Tuesday, the 4th of August 1998, wind and current conditions in the channel were perfect. The tow-out of the new tunnel element started uneventfully. By midday, element 12A had been guided into position. At 3:30, pumps added ballast, slowly sinking the unit beneath the waves. Then, suddenly, something went very wrong. The segment started to tilt, and then collapsed. A huge explosion of water blasted 30 meters into the air. The segment plunged to the bottom. Crews on the pontoons shut down all power, fearing they'd be electrocuted. It was hours before they figured out what had gone wrong. The verdict was human error. A steel plate hadn't been sealed correctly. Water pressure had forced it open and flooded the segment. The winches weren't able to hold the added weight. Luckily, no one was injured. But what about tunnel segment 12A? Extensive testing confirmed it was still usable, but valuable time had been lost. Oresund's builders could have chosen a different method to build their tunnel. They could have bored a tube under the seabed. This is what Denmark did 2 hours away from Copenhagen, where rail and road needed to cross a channel called the Great Belt. This was the site of a disaster far worse than the Oresund's. To dig the 2 train tunnels, they brought in 4 enormous boring machines, each 90 meters long. The front end is a drilling head weighing over 100 million kilograms and measuring 7 meters across. The cutting head chews up soil and boulders. An auger shuttles the ground bits to a conveyor belt, and they're eventually dumped on a small train. As each tunnel boring machine worked its way underground, it also installed pre-made wall segments, 62,000 of them. The problem with boring was that the ground could be unpredictable, and this was how disaster struck the Great Belt. A boring machine hit a water pocket. At first, water began to drip in. Then it started to pour. A special safety hatch should have contained the flood, but it had been left open. Water flooded one tunnel, crossed through the emergency tunnels, and flooded the second. It took a year to get the project back on track. The tunnel here differed from the Oresund's in another way. It went right across the channel, so heavy trains wouldn't have to use a bridge at all. This gave engineers more design options than they had at the Oresund. They were able to build a suspension bridge, and they did so in a big way. The second largest in the world, spanning nearly 2,700 meters. The towers reach up 250 meters, almost 30 meters taller than the towers on the Golden Gate Bridge in San Francisco. Unlike the Oresund, this bridge's structure depends on 2 main cables draped over the towers. These monster cables are almost a meter thick and around 3 kilometers long. The main cables are actually made up of over 18,000 wires, each thinner than a pencil. They're not twisted together, instead they're stretched next to each other and bundled. The finished cables weigh over 9.5 million kilograms each. The trick to making a suspension bridge is anchoring each end of the cable. For the Great Belt Bridge, the